Welcome to Intro to VOPS Part 2, Random and Noise. In almost any kind of VFX shot, we will need variation in the way the simulations behave. This is achieved through adding noise and randomness to various attributes. Now we can go over a very important node, which is going to be the random node. So I have a simple setup here. Basically we have a grid which has quite a few subdivisions, and then I have a sphere. Then we are using the switch node, so we can easily switch between these two types of geometries, so we can see how the random will affect different types of geometry. Then we have a scatter, so at any point I can turn this on and off by using Q, so we can either see how this works on geometry, or we can see how it works on just simple points. And then finally we also have a color, just so we don't have the black points. And also I will press D in my viewport, and let's go to background, and I will just change the color scheme here to dark, so we can see this a little bit better. So we will go ahead and drop an attribute VOP, and let's dive inside. So the random is actually a very simple node. If I drop this, we can see that we have this pause input over here and the random output. So this pause is basically the seed. So if I promote this to a constant, and we can use any value here, if I want to see what the output will be here, let's do a bind export, and we will just export this to an attribute called test. And if I go in the geometry spreadsheet, we can see now that this is going to be the test values. And if I change this constant here, we can see that we still get the same value, and this is because we are using the same constant value for each point. So this is why we are not getting a random value per point. So if for example I were to plug the position inside this pause, now we are starting to get random values, and we can see that these all will range from almost 0 to a value of almost 1. So this is what the default range for this random output will be here. So since the position is different for all of our points, this is why we'll get a random value for each point. Now, even though it says pause here and this is a vector input, the most common use case of this random is going to be in combination with the ptnum, so the point number. So if I plug this inside the pause, we can see now that this changes actually the signature, and it's switched to this blue value, which is now an integer. And now this pause input here became an integer. And we can see if I plug the position back in here, we also get a different signature with different options here. But like I said, most commonly the random you will use in combination with this ptnum. So let's plug this here, and now the signature became 1 the integer input, which it is, and 1 the output. So aside from float values, and let's go back here, we can also change this to give us a random 3D vector. So if I switch this to a 3D vector output, we can see now that the test became a vector that has random values on all of the components that range from 0 to 1. So this is also a good way to get random vectors. And we can go ahead also in the scene view, and since this is a vector, I will just output this 3D vector as our normal. So now I can turn on the normal display here, and we can also preview this 3D vector. And we can see that this does give us in fact a random vector, but they're all kind of pointing outwards. And especially if I look in a front view here, we can see that these are all of the vectors, and they are all pointing upwards, and also a little bit on the z direction. So they are all a little bit skewed, so they're not completely random. And this is because when it comes to vectors, in order to get a complete random vector, we also have to use the negative value. So some of these directions will also need to push in negative values. So if I go to the geometry spreadsheet, and let's maybe just disable, let's not export our test attribute, and just look at our normals. If I just isolate one component, we can see that all of these ranges will go from 0 to 1, so we actually need them to go from -1 to 1. So back in my scene view, I can do a fit range over here, and by default this will now turn into a 3D signature fit range. So our source min and our source max ranges are from 0 to 1, and we need to remap these to -1 and 1. So on this destination min, I will just go ahead and drag this down until we get -1 on all of our components here. And now we can see in our viewport that we have a true random 3D vector. So if I press spacebar 1 to go in the perspective, now we actually have complete random vectors. Now all of these have different lengths, and normally we have to normalize the vectors, so they have a unit length of 1. So if I drop down a normalize, now they also have the same length, so this is more useful for us. But we will talk more about this normalize when we get to our vector operations, so don't worry about that for now. So anyway, I'll get rid of this. So we can output a 3D vector, we can output a 3D point, which is almost exactly like a vector, so I don't really know what the difference is here. I usually just use the 3D vector output. And 3D normal as well, we can see that if I switch this, it does the exact same thing. So I don't know why these two are here. And finally, if we go to the 3D color, and if I remove this connection, I can plug this in our CD, and we can see that we have a different color for each attribute. So sometimes this is useful. And finally, we have this 4D output, so we can also output a vector for attributes, so something like a quaternion, but we will get into this later. The most common ones are of course going to be the 1D output and the 3D vector, so these are the ones that we should focus on. So these two are going to be in probably 99% of cases. And specifically when we are working with random, we are going to use this 1D output, and this is when we actually want to randomize a value per point, and this comes up a lot in particle simulations. So for example, let's go up and let's disable the scatter, so we are working with geometry, and turn off the point normal display. Let's plug this inside a PopNet. So we're not really gonna spend a lot of time talking about this, we're just gonna use the basic setup that Houdini gives us. And if you've seen the intro to Houdini, you know that we can use the attribute VOP to create a velocity vector. So if I just do a simple constant here, which is going to be a 3 float, and I point this vector up, so 0, 1 and 0, and I plug this inside the velocity. We can also preview the velocity by using this point trail display, and if I zoom in on one of these points, we can see this is going to be our velocity vector. If I use this as the velocity and go up and I preview the simulation, we have this result. So all of these now are going at the exact same speed. And let's say that I want each point to have a different speed. If I go back inside, we can use this random value, which is going to be from 0 to 1, to multiply this vector with. So if I drop a multiply after the constant and I plug the result of this random, if I reset the simulation, now we can see that all of the points are going at a random speed. So this is very useful, like I said, with particle simulations. And let's go ahead and also check how this would affect a geometry version. So I'm going to go ahead and put this PopNet to the side, and let's go back to our attribute VOP. And we disabled the scatter, but let's go ahead and switch to our sphere geometry. And let's go back inside here. I'll remove all of these, just keep the random, and let's do another displace along normal. And about this node, we don't actually have to plug the input position and our normal inside the inputs over here. Houdini will automatically recognize the inputs here, and all we have to do is plug the display P inside our P. And now I can promote the amount to a constant, and I can push the points along their normals. So if I grab the random value and I plug this inside the amount, all of these will be displaced by a random value from 0 to 1, and of course we can now use a fit range after our random, and our source min and max are set alright, so 0 to 1, and now I can increase the destination max, so I can increase the spread, or I can even decrease the destination min, so I can push some of these in that are closer to a value of 0. Let's reset these values, and also I can play around with the source min and max, and this is something you will do a lot when it comes to random. If, for example, I increase the source min, we can see that we can grab a lot of these values and turn them to 0. So if I really increase this, we have this very interesting spiky result, and now I can also play with the destination max, so we can get some really cool results. Or if I were to increase the source max, I can kind of increase the spread of our source values, so I can make all of the spikes a little bit more uniform. So the random again is used a lot in combination with the fit range, and of course we can still add a RAM parameter after over here and have even more control. So very useful, and this is the random. Now there's also a different version of random, which is the Gaussian random. So if I drop down the Gaussian random, this will also take a seed, so I can plug the ptnum into this, and if I plug the results in our amount here, we have kind of the same situation, but if I decrease this, so what the Gaussian random will do for us, it's going to give us values that also go in the negative directions. So it's not going to be from 0 to 1, it's going to be values around 0. So maybe this makes a little bit more sense if I do a bind export and I do the test attribute, if I go inside the geometry spreadsheet, we can see that the values range from 1 to a value of -1. So this also goes over 1 or -1 if I increase this STD deviation value here. So if I increase this, we can see that we are pushing these values even further, and we can see how this affects our geometry. If I push this further, we get both negative and positive values, and this value here controls how far apart these values can be. So if I go to the geometry spreadsheet, if I decrease this value, we can see that our highest values will be around 0.2 and -0.2. So this node is also sometimes useful. Specifically, this node, let's go ahead and disconnect this. This Gaussian random can also have a 3D vector signature. So earlier when we generated the random vector with the regular random node, we had to fit the ranges from 0 to 1 to -0 and 1. And now this output will directly give us those negative values. So we don't have to do the fit range thing anymore. This will be a true random vector. So if I plug this in my test, we can see that we have these negative values as well. And if I plug this inside our normal, let's go ahead and turn on the normal display. Let's maybe switch back to scatter. Now this is a little bit hard to see because we are working with low values. So I can go to this Gaussian random, and I can just increase this deviation so we can push these values out. And now we can see that we have a true random vector, and maybe I can switch this back to my grid. So we can see that all of the vectors are truly random. So this is usually what I use this Gaussian random for, mostly to get a true random vector, so I don't have to do the random and then the fit range after. I just use the Gaussian random instead. But any other time I would probably use just a regular random. So the random node does have its place, but if we want something a little bit more complex and with more options and interesting patterns, we are going to use a noise. I'll go ahead and let's get rid of all of these. So we have the same setup here, which is going to be this grid or this sphere, and let's go ahead. Let's maybe work on our sphere for now. So I will set the switch input to 1, and I'll disable the scatter, leave the color on, and we have our attribute VOP. And let's go ahead and let's do a turbulent noise. So let's drop this here, and just like the random, it's going to need some values from where to generate these noise values from. So 99.9% of the cases we are going to use our own position. So I'm going to plug the P into the position, and by default the turbulent noise is going to give us a signature of 1D noise. Let's go ahead and take a look at this 1D noise, and we will export this to our color just so we can preview this in our viewport. And maybe I'll press D, and I'll set the background back to a light value. So we have this nice pattern, and we can play around with the frequency and the amplitude here. All this is doing is basically just doing a multiply operation over the values that we already have. Maybe I will go up and I want to increase the resolutions here. So let's maybe do 100 for our frequency on the sphere, and we will go back. So we also have the offset if we want to push the noise along any of our 3 dimensions. So I can push this on the X or Y or Z, and this is also a very cool way to animate the noise. So if I plug the time into a float to vector and plug this as my offset, we can see that we have this nice noise animation that's animating on one of the dimensions, and I can use any dimensions here. So this is actually a very common thing when you want an animating noise. You will probably use the time or frame to generate this offset vector. So let's go back to our noise settings. Then we have attenuation and turbulence. So turbulence will sort of increase the detail of our noise, and we can see if I set this to 0 and start increasing the levels, it sort of adds more levels to the noise, but usually I don't really mess around with turbulence. I kind of like to leave the setting as they are, and if I want more detail, I will usually increase the roughness. So if I increase the roughness, we can see this will do exactly what it says. It will add more roughness to the noise, so it's going to add a lot more high frequency details. And if I want a smoother result, I will just set the roughness to a lower value like so. So usually I play around with the roughness and leave the turbulence as it is. And if I decrease this attenuation, we can see that this kind of flattens the values of our noise. And in fact, if I go to this question mark icon over here, so we can go to the documentation that Houdini provides. We can scroll down here, and this is actually a pretty good documentation. We can see we have a lot of information on noise, but if I scroll further down below, we can find our attenuation. So it flattens the noise to prevent extreme spikes by damping the values. Higher values create a smoother look. So like I said, it kind of flattens the values, but I don't find myself usually adjusting this attenuation value. I usually keep this at 1 and don't touch it, and also the turbulence I keep this at 5 and don't touch it, and I play around with the frequency, offset, amplitude and roughness. So the noise can be many types, and the default for the turbulent noise is going to be this alligator noise, which gives us values that range from 0 to 1, and we can see the pattern that this creates here. So all of these types have pretty specific uses, and you will really get to know them once you start using them in your projects. So there are quite a few types, and all of these are a little bit different, as we can see. But as far as turbulent noise goes, the one I find myself using the most is going to be the simplex noise. So this gives us values that range. If I go in the geometry spreadsheet and check any of these components, we can see that we get something between 0.6 and a negative 0.6. So what I usually do in order to work with ranges from 0 to 1, which will be more useful for us, is after the turbulent noise, I almost always do a fit range, and we set the source mean, like I said, to a value of negative 0.6 and the source max to a positive 0.6. So now in the geometry spreadsheet, we are roughly getting values between 0 and 1. So this pattern or this type is what I usually use to break up the sources when I do simulations, so mostly particle simulation. So like I said, all of these types have their use cases, but simplex noise will be the one I use the most, especially if I'm using the 1D noise signature. And speaking of which, let's set this to a 3D signature and see what we get. So I will remove this connection, and whenever we are outputting a 1D noise, so a float value, we are usually exporting the value directly to our attribute. So I can do a bind export, and this can become something like density in case of a smoke simulation, or like I'm doing here, I'm plugging it inside the CD. But when we are working with a 3D noise, so I will set the signature here to a 3D noise, usually we want to add this on top of our position. So let's go ahead, and if I check the result of this noise in the geometry spreadsheet, we can see that we are getting roughly the same values. Now if I plug this directly inside our position, we are getting exactly these values as they are here. So this is not really useful for us, so this is why we usually add it on top of the position that we already have. So when we add this, now we can see all of these nice patterns that it creates. So we still have the animation. If I scroll my timeline and if I go in the turbulent noise, we still have pretty much the same properties that we can adjust here. So these are pretty self-explanatory. I'm not going to go over them again. Again, roughness will add more detail or smooth out the noise. And then we have amplitude and frequencies. So you should be already familiar with all of these. And again, as far as turbulent noise is concerned, even when I'm doing a 3D displacement, as we are doing here, adding it to our P, I will usually use the simplex noise version, but sometimes the sparse convolution noise also gives us pretty interesting result, and this is mostly used when you are trying to create a terrain or some rocky geometry. So we can see what this does for us. It really creates some nice interesting patterns, and it's it kind of has a little bit more dramatic changes than the simplex noise. So I would say that the values of the simplex noise are a little bit more closer to each other, whereas if I change this to sparse convolution noise, we see that we have a little bit more interesting look with some peaks that really stand out more than the rest. And we can also go up, and I will turn on the scatter so we can preview this on the points. And again, I will press D, and for the points I will make the background dark, and maybe I will just increase this to, let's do 1 million, so we have enough points. And also I will right click this icon over here with the material and change the display to pixels, just so we see our pattern a little bit better. So this also comes up a lot of the time. You will have sources in your simulations that are just points, and you want to introduce noise to those sources. So again, usually I will do a turbulent noise, and I'm either gonna use sparse convolution noise or simplex noise. So if I increase the amplitude here, we can see that this actually creates a very nice interesting pattern. And when we combine this with animation, we are really going to set up our particle simulations to have interesting motion. The main problem with turbulent noise is that we can only animate this noise by using this offset value here, which is essentially just shifting basically the positions over one of the x, y, and z directions. So no matter how we animate the noise by using the offset, we are always going to have this sort of directional movement. So if I want to evolve the noise over time, we can use an anti-aliased flow noise. So if I drop this, let's search for anti-aliased and let's use the flow noise version, which gives us a couple of extra properties. And if I were to, let's plug our P inside the position, and if I were to replace our turbulent noise, we can see that we kind of get the same result. Let's also make sure that this will be a 3D output signature. So let's switch this to a 3D noise. So this kind of looks the same as our turbulent noise. But now we have a couple of options here, a couple of extra options, which are going to be the flow and the flow rate. So I can use this flow value to animate our noise, and I can simply plug our time into this flow value. And now if I look at the animation, we can see our noise is moving, but it doesn't have any particular direction. And now our flow rate, if I set this to a value of 2, so if I increase this, the movement will sort of have a higher frequency. So we can also have larger, broader movement if I set this to a lower rate. So when I preview this, we can see how the flow rate will affect our movement. The problem with animating the noise with this flow value is that this is a repeating pattern. So if I set the flow rate back to a value of 1, let's maybe disconnect our time. If I set this flow value to 0 and check my noise, and if I set this to a value of 1, we have the exact same pattern. And also when I go to a value of 2, it will again have the same pattern, and this is because we are going to repeat the animations from 0 to 1, and then from 1 to 2, and from 2 to 3, and so on. So it's going to be this repeating cycle. So if I plug the time back into our flow, to me this is pretty obvious that it's a pattern that keeps repeating, and depending on what you're doing, this might be enough. But the better version is going to be by using a 4D vector instead of a regular 3D vector. And when it comes to noise, all this 4D vector means is that it's simply going to take the position and it's going to add the fourth component, which is going to be the time. So usually a vector with 4 components is going to be a quaternion, but we don't need to worry about that for now. When it comes to a noise, if we want to generate a 4D vector, all we have to do is add the noise to our original 3D vector. So if I go to this flow noise, we can see that the signature here can either be 3D input 1D noise, so it can either give us a 1D output or a 3D output. But if I were to disconnect the position, so if I were to cut this wire and I go to the signature over here, we see that this also gives us now an option to input a 4D input, so the vector with 4 components. So let's switch this to 4D input and 3D noise. And now we can see we have the 4 components. So the first 3 is going to be our regular position, and the fourth one is going to be the time. So to create this, let's drop a vector to vector 4, and we will plug the position inside our vector input and our time as our fourth component. And now we can plug this into our position, and when I play now, we will have the properly evolving noise. So now we no longer have a pattern that keeps repeating, so this will give us a better result. Now it's important to note here is that when we want to change the frequency, so if I want to increase the noise pattern, so get more high frequency details, and I increase the frequency, this will also make our noise evolve faster because we are also increasing the frequency of the time, so our fourth component here. So if I play this, and let's maybe just increase this further, we have a higher frequency over the noise, but now also over the time. So for example, if I were to keep these 3 values as they are and change our 4 value to a value of 0.2, we can now see that the noise evolves a lot slower. And if I change this to a value of 5, we will have a much higher speed. So this is something to keep in mind. So I will sometimes use this noise type when I want something specific in terms of animation, and I don't want the noise to have an obvious directional movement. So this is when I would use this AA flow noise. Now curl noise can also have this kind of 4D vector input, so I will get rid of this flow noise and I will do a curl noise, and I will plug the result of of this vector to vector 4 inside our pause. And when I do this, we can see that this the inputs here switched from green to yellow, so it automatically got set to a signature for the noise. So this is also something worth knowing, and I will set the noise type here to simplex, which is going to be my favorite one, and I'll get rid of this connection, and let's add this, and I'll actually get rid of this turbulent noise, and let's add our curl noise. So this is again sort of similar to the flow noise, and by having this 4D input we can see that we also have animation, so the same rules will apply here. As I change the frequency, I can decrease the speed here if I set the fourth component to a lower value. So we can do something like this. We can see, I'm not sure how noticeable this is in the viewport, let's maybe set this to a point display. If I play the animation, we have these stray points that are flying around our geometry, and this is because of this step size here. By default this is a very low value, so if I just increase this a bit to maybe a value of 0.01, we can see that this actually got rid of that flickering. So usually you have to increase the step size a little bit to ensure that you don't have any weird artifacts. So let's go back to pixel display, and this curl noise is extremely good at achieving fluid motion. So this is kind of imitating how a smoke simulation behaves. So for example, if I go up and I do from this color, let's drop this inside a solver. And this will be the exact same thing that we did in the intro to Houdini video. I will grab this attribute VOP, let's go to our solver, and I will just place this inside, and we will link this to our previous frame. And let's go inside, and I will actually right click and choose to promote all of the input parameters so I can edit these at the top level. Let's go ahead and just reduce the amplitude. So now this amplitude will accumulate over time, and since this is using a 4D vector, this is also evolving the noise. So if I play now and check out the animation, we see that we end up with this really nice fluid and organic motion, and hopefully we can see now the application of this curl noise. So I can maybe decrease the frequency slightly, and let's reset the simulation. Okay, we have to go up at the top level, and I will pin the viewport to the sub level. So let's go back inside and let's play, and I can maybe decrease the frequency even more, and again we have to go up and reset the simulation. So we end up with this really cool organic motion. So usually when I'm inside a PopNet and I'm creating or adjusting the velocity, a lot of the times I also add this curl noise on our velocity to get this really nice organic motion. So let's go back to our regular attribute VOP and let's step back inside. We can see we also have some extra options here: surface effect radius, distance to surface, surface normals, and all of this. But these have more to do with volumes. And with these settings we can get different geometry to interact with our curl noise, and we can create nice organic swirly motion that goes around the surface of any given geometry. So it comes super handy when creating velocity fields, but this is something that we will discuss in the volume chapter. So for now we will only use the regular options here, so more of the classic noise properties. But yeah, curl noise is also one of my favorite types of noise, and it's really good and especially useful in simulations. Finally, I want to talk about the Worley Noise. So you might also find this type useful. For the Worley Noise, let's maybe go up and I will switch this. Let's leave this as a sphere, but let's work on the geometry. So I will turn off the scatter node. Let's go back inside and let's maybe just get rid of all of these, start fresh, and we will drop down the Worley Noise. So we have sort of the same inputs. We can generate this from our position, and we have a lot of different outputs over here. So if I plug this to one value, so our first output inside the color, we can preview what this noise does for us. And essentially what the Worley Noise does, it scatters a bunch of points all over the geometry, and it computes the distance from those points. So this is why we are getting this sort of cell-like pattern, and we can change the way this distance is being calculated. So we have this, however this is pronounced, and then we have Manhattan, and then we have another one that I'm not gonna dare to pronounce, but we have these three methods to generate this distance value. But more often than not, probably 95% of cases, it's going to be the first one, which is again, I'm not gonna try to Euclidean, I don't know. But anyway, it's this one, it's the first one, it's the default one, so this is the one we usually want. Now we have this distance 1, and if I plug distance 2 inside the city, this is sort of the reverse. So previously we had dark points that increase the gradient to outside, and now we have the reverse where we have white values where our cells are, and it's going towards a value of black on this gradient. So by itself, let me just plug the dist 1 value inside the CD. By itself, this is also pretty cool, and it's something that you can use to create very interesting patterns. And also a cool trick here is we can actually add a regular noise to the position from where we generate this Worley noise. So if I do a turbulent noise and I generate it from the position and I add it to the position where we generate our Worley noise, so I will drop an add node here. This turbulent noise will need a signature of 3D noise, and let's use for noise type sparse convolution noise, and I will plug the result inside this add. We can see now that this turbulent noise is sort of combined with our Worley noise. So if I reduce the amplitude here, maybe we can see exactly what's happening. As I increase the amplitude, we are distorting the position from where these cells are being generated. And as a result, it has this nice combination with the Worley noise. So this is a little bit different than if I were to generate, I'm just gonna duplicate this, and if I were to generate a 1D noise, and since this is a float value, I can do a multiplication here. I will disable my add noise for the 3D turbulence, and this is just to show you that if I were to multiply this directly on our output of distance 1, we are not getting really the same result. Even if I do a fit range here and I fit this from 0 to 1, we are simply doing a multiplication. So this would be sort of like how we would do it in Photoshop. If I were to add a turbulent noise over our pattern, this is pretty much what happens, but let's get rid of this. When I distort the actual 3D position from where the Worley noise is generated, we have this very natural forming pattern that's a combination between Worley and turbulence. And of course, this doesn't have to be a turbulent noise here. We can still use any noise. So if I do a curl noise, this will be by default 3D signature, and add it to my position, we can see we have a different result entirely. So if I start to increase this, we can really start to experiment, and there are really a ton of ways that you can get a lot of different patterns. So this is just to give you an idea. Let's maybe undo this and use the regular turbulent noise here. So we can use this to output a float value, but of course we can use this as well to modify the position. But if I were to apply the result of this distance 1, if I were to add this the same way that we add our turbulent noise, let me maybe get rid of this CD connection. If I plug this dist 1 here with a simple add operation, we have a pretty cool result, but we can see that all of the values are skewed in a certain direction, and this is because we are outputting float values. So we are essentially having the same value on all of the components of the vector. So this is why we are getting this result. And a better way to apply this in a 3D position, let's get rid of this. We are going to use displace along normal, and we will use this as our amount. So if I plug this displace P in our P, now we sort of have a uniform distortion. So this would be kind of the result that we are expecting, and I can play around with the settings. And these operations that I did here, this is the basis for a very cool rock formation that you can do. So maybe if I decrease the frequency and I increase the scale of our displays, we can see that this already starts to look like a rock. And I can go to my turbulence and make some further modifications here, maybe reduce the amplitude. So we can see that this already looks kind of like a rock. Then we have different combination of the dist 1 and dist 2 values. So for example, if I do a subtract, I can subtract these two values to get a different pattern. So we get something like this, which is also pretty interesting. And I can reverse the order of operation here. So this matters when we are dealing with subtractions. If I press Shift R to reverse the order, we see that we kind of get the inverted result of what we had previously. So this is also, we can see this is a very cool pattern that can be the basis for a rocky texture. And then also we could simply layer a bunch of these noises. So if I hold Alt to duplicate this, I would be able to add this, just the simple distance on top of what we have. And if I do a multiply constant on our second Worley Noise, I would be able to control this individually. And hopefully this gives you an idea of how this Worley Noise is useful. Alright, so this is for geometry. Let's maybe switch to points. So I will turn on the scatter, and this will no longer work since our scatter by default doesn't have any normals, but it doesn't matter because let's go ahead and get rid of all of these. I want to show you one final thing. Let's do another Worley Noise. We also have this seed, so those cell points that we scatter to generate the distances. So this is basically what dist 1, 2 and 3, this is why they are called dist. It's because it's referring to distance. So all of the points that we scatter to compute these distances will have a seed. So if I plug this in the CD as it is, we get a weird result, and this is because if I do a bind export and I export this to a value and I will just name this seed, we can go in the geometry spreadsheet and we can see that by default these seed values will be really super high values. So we are working with like hundreds of millions. So this isn't really that useful for us in this format, but what we can do is we can actually, since this is different per cluster of points, we can use this as a seed to generate a random value. So what I can do is I can plug the seed inside a random, and now if I plug the random inside the CD, we have these nice clusters that we can use to drive all types of different effects. And maybe this will be more noticeable if I just apply it to the geometry, and maybe I can even increase the frequency even further. Maybe let's try 200. Okay, so basically the point that the Worley Noise scatters will be right in the center of these points, and then based on what point is nearest to that scattered point, it's going to be assigned a seed. Later I will actually show you how we can do the scatter ourselves and compute this distance. It's very simple, but it will come in a different chapter in this VOPS series. But anyway, I can still go back here and I can still even apply a turbulent noise to this. Of course, this needs to be a 3D noise, and let's use sparse convolution. We could use simplex as well and it would work. So let's plug this here, and maybe I can reduce the amplitude, and we can create a more organic pattern like this, increase the frequency and the roughness. And this clustering is super useful, for example, when you are dealing with constraints. So if you are doing an explosion over some geometry and you want some of the pieces to stick together in a certain formation like this, we can use this seed value to generate these clusters on the constraints. Or we could even use this if I plug this in a displace along normal. Even this will work and it will give us a pretty interesting result. Let's go ahead and plug this in the P. Okay, so we have this result, and I can adjust this further. And we can go back to our Worley Noise and do some interesting patterns. So we can generate kind of like this cracky surface with this Worley Noise. If I go up and I switch this to my grid, maybe we can see this better here. And of course, I can increase the subdivisions. So this seed value can also be used when you are creating rocky textures and terrain. So hopefully you can see how this is useful and some different cases of where you would want to use the Worley Noise. Now, there are more noises and more types that I can go over, and maybe I will make a separate video dedicated to those, but usually these are the ones that you will use on a daily basis, especially the turbulent noise and the curl noise. I use those almost every day, and then sometimes Worley and AA flow noise. So this is why I wanted to cover these 4 types and give you an idea of what each one can do. The next node that I want to introduce is going to be the relative to bounding box node. And this isn't directly related to the random or any noise function, but I didn't know exactly in which category I should put this, so I might as well talk about this here. This is one of my all-time favorite nodes, and let's just do another attribute VOPS so we can start fresh, and I will just point this scatter here. So let's remember that we are either working with a grid or a sphere, and we have the option to turn the geometry into points. So let's go to our attribute VOP and let's work with just geometry for now. So I will turn off the scatter, and inside here we can drop the relative to bounding box. So what this node essentially does is it's drawing a bounding box around any object that we have, and it's returning the x, y, and z value. So if I go up, let's maybe do another type of geometry. Let's drop a rubber toy test geometry, and let's look at this instead. So if I plug this into a bound SOP, I can template the result of this by pressing E. So this is the bounding box that it draws over our geometry. So the relative to bounding box node is going to return these dimensions, and it's going to map all of the axes to values that range from 0 to 1. So if we look in a side view, in any of the side views, this will be the Z size. So no matter what values the position of the geometry has, it's going to map those values as we did earlier's examples when we split the position vector and we grabbed one of the components and then we used a fit to remap a value. So in this case, if we are splitting the position vector and we are grabbing the z component, we would have to use a fit range that goes from 1 to -1, and we would remap those to 0 and 1. So the bounding box automatically does this for us. And no matter what geometry we are working with, so we can see that even if I were to scale up our rubber toy, we would still get this bounding box that fits our geometry precisely, and we would have values that range from 0 to 1 on all of the 3 components. So no matter how tall this is or how wide the geometry is, we are going to have 0 to 1 on the y and 0 to 1 on the z, and for the x component as well. So when I go back to this attribute VOP that's working on the sphere, and let's untemplate the bound, let's step inside. So we want to generate this from our position, and for the file we can either point this to op input 1, which is ourselves, or if we want, we can set the input here to be first input. So now we no longer need this connection. So this will output all of the 3 vectors at the same time, and we can even preview this. If I plug this inside the CD, we can see that we get a gradient in all of the directions at the same time. Now this isn't particularly useful to us. What we usually do with the relative to bounding box is we are splitting the vector. So if I remove this connection, let's do a vector to float so we can split all the components. And for example, now if I plug the second component here, which is our y dimension, in the CD, we have this value that goes from 0, that's all the way at the bottom, over to 1, all the way at the top. So this is super useful, like I said, because we are going to have this result no matter what geometry we input or how we change it. So even if I were to animate some of these values here, the relative to bounding box will always fit the values from 0 to 1. So this is extremely useful. Let's maybe set this back to a 0.5 radius. So after we decide which component we want to use, we can then use a fit range to further control this. So if I drop a fit range, I can control the source min and the source max to sort of squeeze this gradient together and get a sharper contrast. And I would be able to also plug a ramp parameter after. So let's go ahead and set this to a spline ramp, and I will go up so we can edit the ramp, and I will reset this. So now I can do further modifications to our ramp here. And let's maybe grab all of these handles by holding down shift, and let's set the interpolation to B-spline so we get a smooth result. And I'll press D maybe and change the background back to light so we can see this gradient better. So if I go back inside, we can create some really cool controls here. If I were to promote the source min and the source max as well, and also I can offset these values if I simply add to the second component here. So after we split the vector, if I drop down and add here and I promote the second input to a constant, I can rename this to offset. And this is something I do all the time in order to create an attribute that travels the geometry. So if I go up and I go to this offset, if I decrease this value or increase, we can see how our values go across the geometry. So this is very useful when we are doing attribute propagation, and it has a lot of use cases. And also now I would be able to go to this ramp as well, and if I make the last handle here, if I turn this to 0 as well, we are left with just this stripe over here, and maybe I can adjust the ramp a little bit. And if I play around with the offset, we have this cool result. So this could be sort of like a trigger for all of the points if we were doing a particle simulation, and we would still be able to adjust the minimum and maximum ranges here. So we really have a lot of control, and let's maybe squeeze this back together, and let's remove this handle, and I'll reset this to the original look that we had. So maybe I'll get rid of some of these handles. And by the way, you can remove any of these handles if you just hold down click and drag it down. So if I go back inside, I can use any of our components here. So if I want, I could use the direction on the X or the direction on the Z, and we would have the same result. And also we can add some noise to the position from where we get our bounding box. So the same way that we did with the Worley Noise, let's do a Turbulent Noise, but really you can use any type of noise as long as it has a 3D signature output. So now I will generate this from this position, and I will just add this on top before we plug it in our relative to bounding box node. So I will add this here, and we can see how easily we can also introduce some noise into this gradient. So if I play around with the frequency, or I change the type, and I can even increase the amplitude if I want more noise overall, and play around with all of the settings that we are familiar with now, and we can really get some cool and super fast results, as we can see. So now if I play around with the offset, we can see how easily we can create this growth animation. So super useful node relative to bounding box. I use this almost every day, and this is why I wanted to show this early on.